Welcome back to Introduction to Computational Fluid Dynamics, CFD. I'm Professor Steve Miller. Today we'll talk about the basics in terms of terminology, layout, and computing for parallel processing, otherwise known as parallel computing. In the previous class, we finished up our turbulence module and we discussed direct numerical simulation, that is the direct integration of the Navier-Stokes equations with our basic numerical methods, or more advanced ones like pseudospectral methods. We also estimated the amount of computational power it takes to run a DNS simulation. We also discussed the idea of LES simulations, showed some examples. Remember, this is the idea that we spatially filter the domain to only obtain and resolve large-scale turbulent structures. The smaller scale structures are, of course, modeled with one particular approach like Smagorinsky. Alternatively, we might look at the Miles approach, where we integrate those scales away numerically. They let them dissipate numerically. Today in this class, we'll have an overview of parallel computing from a big picture, and I'll outline key terminology that you'll need to know to operate your CFD codes in the contemporary environment of supercomputing or simply parallel processing, even on our more advanced workstations and desktops. It'll focus more on concepts and terminology. We'll also talk about memory architecture, which is very important when discussing parallel computing. Finally, we'll look at some of the more contemporary computers today in the top 500 list and discuss them. Now, we would like to provide some sort of overview of the broad topic of parallel computing, but this is a field in itself. There's many mathematicians and computer scientists and engineers who design both the hardware and software to drive parallel computing today, to integrate thousands of CPUs and memory banks together seamlessly to make a supercomputer. We'll only be talking about the major terms of this approach through the viewpoint of a user of the particular system, enough so that you can understand how it works. This portion of the class is based on Lawrence Livermore's Computing Getting Started workshop, and I recommend you go to this particular webpage where, of course, I'm discussing many of their figures shown here. Let's first look at the classic serial computing approach from a big picture. Now, traditionally, software has been written for serial computers and computations all the way since the 1950s, when, of course, digital computing was really taking off and the golden age of computing started. Now, a typical problem, just like an equation solved on a computer, would be broken down into discrete series of instructions. This is exactly how you've learned to program, of course, in many of your college courses, and how we teach it generally in our department. We don't usually consider parallel programming. Now, our instructions are indeed executed in a sequential order, one after another. This is the idea, that we take the problem, break it apart, and execute each part sequentially. For some problems, we have to do serial computations. The nature of the problem cannot be done or performed in another way. And they would always be executed on a single processor. So serial computing means that it's running on a single processor. That is, the code that you've written and compiled and are running is running on a serial processor, one processor. And only one instruction can be executed at one particular time in a serial computation. So you can see a typical problem might be seen as a block, and we break down the block into, say, n components, T1 to Tn. These were run and sent to the, of course, processor in a sequential order. Now let's consider the idea of doing this process in parallel. In the most simple sense, parallel computing will be the simultaneous use of compute resources to solve a computational problem. In our class, of course, we're looking at it as CFD. So the problem must somehow still be broken down into sequential parts. So it could usually be solved concurrently instead of sequentially. That is, two particular instructions might be executed at the same time, and then the next pair. So you can see many problems, as you might imagine now, cannot be necessarily broken down in a sequential instruction order. So some problems would be very difficult to parallelize. Now, each set of instructions would likely be executed by a particular processor. You would need more than one processor now to run, of course, a parallel program. And they would be running in parallel, that is, at the same time, but two different parts of the problem, if we can break it up, at least. Now, Our computational problems should be able to be broken up in discrete pieces that can be solved simultaneously. That's really a requirement for parallel computing. Anytime you have a code, even if it's not CFD, you have to look at it and say to yourself, can I break this up into different pieces which can be run concurrently? We'll then try to execute multiple instructions at any particular time. And the advantage of this, of course, is if we can divide the problem evenly and compute it on multiple processors evenly, then we should be able to find the result in a faster rate. You'll see that this is not always the case, and a user and programmer of a CFD code will have to be careful on how this is done. Now, the computing resources will typically be either a single processor with multiple cores, or perhaps many processors with many cores, or a network of computers. We'll look at these architectures in a few minutes. Over on the right, we have perhaps a particular problem. We write that in as blue, and let's try and divide it into 4 parts from top to bottom. 1, 2, 3, 4. So each row is its own particular breakdown of the problem, and each column is a step in the process. We take the problem, divide it into 4 parts, and we send the 4 parts of the instructions to each individual processor. So we could divide this in any number of parts we desire if we can parallelize the problem, of course. That is, we could send maybe 50 parts of the problem or computer code or instruction set to all the different processors. This is very difficult to do in CFD. Let's now look at a particular overview of the parallel computing architecture. Now, virtually all particular standalone computers, that is those that are not networked together in like a supercomputer or a cluster, and a cluster is a collection of computers, which we'll see in a second, will be parallel from a hardware perspective only. And that does not mean that the program itself has to be run in parallel. For example, we could have a single CPU, multiple computing units called cores, and these might be running different programs always in serial, or they can be running one particular program in parallel. It's all up to the operating system and scheduling. Now, down here we have a graph of a particular setup which is known as like a cluster. It's really a connection of multiple standalone computers, which we call nodes or blades, depending on the vendor or company making the system, to make a larger parallel computing cluster. This is typically how CFD is performed in this framework on large-scale supercomputers. Now, each computer that is, it's self-contained, and we will call it a node. So this particular case has 6 nodes, 1, 2, 3, 4, 5, 6. And each one has its own block of memory. This could be your typical random access memory on a typical desktop. And then each node might have 1 CPU, and it has 4 cores. Another way to look at it is you might have multiple cores per node, which have multiple cores. Each one individually can operate on its own. The trick here is to manufacture these in large numbers and connect them by a high-speed network. This way, they can all communicate to each other and, of course, divide the problem. For example, I could divide my problem first into 6 pieces across 6 nodes and distribute it through the network. And then each particular CPU will again divide the problem in 4 more parts on each particular node. That's one way to look at it. So in this case, we have 4 times 6. That's 24 divisions of the particular problem. So you might be wondering, well, if I can take my problem and divide it by 24 different parts and send it to different nodes, it should run, of course, at 1/24th the speed compared to the serial program. But you'll see this is not necessarily the case, so some examples we'll look at in class. But nonetheless, this is your most typical and popular setup for a supercomputer using like this cluster environment. It's really called a cluster, and it's a division of nodes with their own individual CPUs and memory. Now, we might ask ourselves, why do we use supercomputing? Why do we use parallel computing? Of course, number one, it would save time and or money. Now, running my code on my own personal laptop would certainly be cheaper than running it on a large supercomputer. On the other hand, running it on a supercomputer would likely be more expensive. That being said, some problems are so large they can't run on my personal laptop, and I would have to run them on a supercomputer. Or if we're running a DNS calculation like I showed, it would be wise to break it down into pieces. So instead of 5,000 years, I might have perhaps 1 year or less if I distribute it across many processors. Most important advantage is I can solve larger problems which are more complex that could ever fit on a particular single node or CPU with its associated RAM. It also provides some sort of concurrency. And I can take advantage of non-local resources. Concurrency means, of course, I can run these codes across multiple systems in the world. And if I lose one, it will not be lost in the total set. I can also take advantage of non-local resources. So if I'm sitting in my office in, say, Florida or somewhere else, maybe in an exotic country, giving a seminar, then I can say, oh, I can still check on my computing resources for my problem, and I can go and tunnel, that is, communicate through the internet, to communicate with one of these particular supercomputing clusters to check on my job. I don't have to monitor it. I can just submit it and let it run. And so it doesn't matter where I work in the world. These computers will be accessible with appropriate security measures. And of course, it makes better use of underlying parallel hardware. Let's look at one of these particular CPUs shown in the previous slide. So these 4 cores, in this case, might be 6. So this is a particular CPU. This is a picture with divisions of the devices. And this one is the so-called Intel Xeon processor with 6 cores. And you'll see this particular CPU has 6 cores on it. It's almost like original CPUs only had 1 core. The core and the CPU were one thing. The marketing groups came along and they looked at cores as their own individual CPUs, which were all together on a single die or piece of silicon. This is all very informal from an aerospace engineer's point of view. Note that those in computer scientists and computer engineering groups and departments would probably be raising eyebrows a little bit. But it's good to use the language used in aerospace engineering and the CFD groups to talk about computers. They'll certainly understand the way we discuss them. There's a little bit of a cultural difference, and that's okay as long as we can communicate. Remember, our focus is on fluid dynamics and physics and the mathematics, and of course, how it's implemented through parallelization. There's a large layer of abstraction between our field and, of course, the hardware and computer science groups. Nonetheless, they're becoming closer over time to emphasize the importance of parallelization on CFD. We've talked a little bit about the motivation for, of course, parallel computing, that we might be able to solve problems that we cannot before at quicker rates. Also, we remember when we looked at our DNS scaling study, we looked at a particular computer to estimate time, and we looked at, of course, a 1 gigaflop per second computer, which resulted in a 5,000-year calculation. Now, instead of parallelization, we could increase the CPU floating points per operation. That's very difficult today, and now more modern CPUs are simply increasing the number of cores and adding more cores and CPUs through the distributed computing network of a modern cluster. The picture on the right shows how performance is increasing with, of course, these large computers that are clusters with time. This particular graph shows the years 1994 to 2014. The video here today is made in 2020, so this is already 6 years old, but the extrapolation and current graphs today look very similar. It looks like a rather linear rate on this particular log linear scale. Now, the 3 dots represent the summation of the top 500 and the fastest computer in the world at the time of the writing of 2014. You can see that summation of the top 500 fastest computers will add up to this green dashed line. It could also be seen that the world's fastest computer in 2014, at least had publishable data, was running at over 10 petaflops, and the 500th fastest was only running at 500. So you can see between the 500th fastest supercomputer and the first fastest supercomputer are 2 decades of consistent performance increase. Now, the race is on today, of course, for exaflop calculations, which means that the whole computer, if it's running simultaneously and using all its CPUs and power, will go at about 10 to the 18th calculations per second for floating point operations. That's amazing. One might look and wonder about what different applications there are for these parallel computing and supercomputing. Well, here we are in this particular emphasis of aerospace, which is fairly small right now compared to other areas. There's a whole wide range, and so if you can understand these concepts, you can apply them to any of these other types of fields. There's a large field of other, which might just be classified as a miscellaneous area, but this is not necessarily true. Remember, some of these things are going to be classified because, of course, the nature of the work. Now, a few important concepts and terminology that you'll just have to keep in mind when communicating with those working with supercomputing and, of course, working with CFD codes in parallel. The first major concept is shown on this slide from Lawrence Livermore National Labs. This is the so-called von Neumann architecture named after John von Neumann. We looked at his stability analysis earlier in the class. Now we turn to his idea and layout of computer architecture, which almost all contemporary computers follow today. Typically, on one particular board, you'll have a controller unit, you'll have the CPU, which contains both the controller unit and the logic unit, which communicates with the memory, which is the random access memory. This in turn is connected to the input and output of the computer. It's that simple. And this type of layout is predominantly used in almost all computers today, and especially the clusters that we're using, even on your cell phone, which you're holding. Now, there's a little bit of taxonomy, and when you're dealing with a particular computer, you'll have to classify and understand which kind you're using. The matrix below summarize it. The first is single instruction stream, single data stream. This is a computer which is most traditional. It has a single CPU with one core, which is just a CPU, of course, and it has a single bank of RAM. Now, we can also have, perhaps, a single instruction stream with like one CPU and multiple data streams. So this could be, of course, that we have multiple banks of memories, in this case, or a way to get data in and out of the CPU. Then we might have multiple instruction streams in a single data stream. This is like a computer where you have multiple CPUs or multiple cores, all with a single memory bank. Finally, in the most general category, you might have a computer with multiple processors and multiple memory banks. These can be, of course, divided in different ways. So if you have a computer with one CPU with classic memory, it's, of course, in the first category. If you have a computer with multiple CPUs and one memory bank, it's in the lower left category. Finally, if you have multiple CPUs with multiple memory, which is distributed, it's likely in the lower right. Almost all clusters today are put into this lower right classification of MIMD, multiple instruction stream and multiple data stream. Now let's look at some particular concepts. The first time you get onto one of these cluster systems, if you have the privilege, you're going to be hit with a lot of terminology, and I'm going to point out the most important ones and try to explain them briefly. You're welcome to read through these slides in detail, which of course are distributed with the class notes. Of course, we generally refer to supercomputing and high-performance computing in the same way, and that means just the general process and field of using the world's fastest supercomputers to solve very, very large problems. We've already talked about what a node is. It's essentially a standalone computer in a particular box. It contains all its own power supplies, CPUs, graphics processor units if needed. They're not needed on a cluster, and of course, memory. It can run on its own, or it can run with other nodes. It's up to the user to select how many nodes the computer should work with. And of course, each particular node has its own CPU, and on that CPU it has a number of cores. For example, I might say the cluster has 128 nodes, 4 CPUs per node, and maybe 8 cores per CPU. You can multiply these numbers through and find out the number of processes, that is, the number of divisions of the problem you can use. In the lower part of the figure, there's some illustrations from Lawrence Livermore. On the upper left is a typical supercomputer. Each one of these little horizontal lines in each one of these racks, so a rack holds a group of nodes, which is usually vertical, and each rack, which is the vertical integration, holds a particular node. And I could slide this node out and look into it and see something like this. Here, of course, there's a memory bank. Here, there's the CPUs. And we could zoom into one of these CPUs, which here is that Intel Xeon, which I showed earlier, which of course has 6 cores. So you can see in this case, there's likely 2 CPUs with 6 cores each. So that means each one of these racks has a number of blades, and each blade has 2 CPUs, and each CPU has 6 cores. It's that simple. This is important to someone using parallel computing because as a user, you will specify how much time the problem is allowed to be solved, That is the maximum time the computer can use. And so if you run out of time, the process just stops. But more importantly, you will specify exactly through an input file of the CFD program or a script file for the computer, or maybe now today a web interface, but I don't prefer such approach because it is another layer of abstraction, the number of nodes, the number of CPUs, and the number of cores which will be used. Now, just because I have a node with, say, 2 CPUs does not mean I have to use both CPUs. For example, if I had a serial job, I could tell and say I want to use one node with 1 CPU and 1 core. If I only want to divide the problem twice, I could say I want to use one node with 2 CPUs and 1 core each, or one node with 1 CPU with 2 cores. Alternatively, I could say I want to use 2 nodes with 1 CPU each and 1 core each. Why would I want to do this last example? Because, of course, I could have more memory. That is, I'm getting the memory of 2 nodes versus 1 node. That is the amount of RAM. Now, tasks are logical sections of the computational work which are broken down. This is automatically done, of course, once the CFD code is parallelized. Typically, a CFD code is written in serial, and it's broken down through additional programming, which represents the parallel processes. Now, 2 of the most important concepts is to understand if your computer has shared memory or distributed memory. Your phones, desktops, laptops, and other devices, which we can't imagine in the future, often have shared memory. That is, all the cores or CPUs in your device can access the same memory bank. There's a specific kind of particular memory, and if it's a shared memory where multiple processors share the single address space and have equal access to all resources, we call that a symmetric multiprocessor hardware architecture. That's typically, of course, what might be in a particular modern computer, desktop, or workstation. Now, if you're running on a cluster, you'll be using distributed memory. And distributed memory means that, of course, that each particular CPU or processor and node as a whole cannot directly access memory of another node. So there'll be the same set of memory addresses on every node of the cluster. But if you want, say, a CPU on one node to access the memory of another, that is, we distributed the problem across all the different parts of the memory, then you'll have to communicate through that and retrieve that part of the memory through the network and store it on the local node. So you can see this is where communication comes in, that we have to use communication to move data from one node to the other, that is, from one bank of memory to the next. Now, our problems are so large they cannot fit on one node. And so this is part of the reason we use distributed memory. We distribute the computational problem in CFD, that's the grid, that's the solution, across many nodes. For example, if one node has 4 gigabytes of RAM, which is small today, and another node has another 4 gigabytes, and our problem is, say, 6 gigabytes in size, it would be very wise to send and distribute 3 gigabytes to both nodes respectively. And that way there'll be more room, that is a gigabyte of RAM left over on each node to run everything else. That is all the drivers of the node and, of course, its own operating system. The next important concept is synchronization. So synchronization means that the nodes and CPUs are all running in sync. This is pretty much trivial to do on a single desktop. But if we distribute our problem to multiple CPUs and multiple CPUs, especially across multiple nodes, that is different physical computers through a high-speed network, then we have to make sure that the CFD solution is being solved in time or the solver synchronized. What does that mean? That means, for example, in a time-dependent CFD simulation, that every CPU is using the same CFL number and advancing in time at the same rate, perhaps. They're all using the same delta t. And one processor is not running ahead of another. So, because of just small differences, some CPUs might be running and solving the problem just ever so slightly faster. And this is due to many different reasons. But there'll have to some computer code or ways to synchronize the result. So far it sounds like there's no downside to the parallel computing other than the extra programming task of parallelizing the code and, of course, running in parallel and distributing. The major downside and the cost is the so-called parallel overhead. Parallel overhead is the amount of time it takes to require and coordinate the parallel tasks. opposed to just doing a serial run. So the parallel overhead is the time it takes over a serial program, and this is often included in many factors. For example, starting up a parallel run, distributing the data across the network to different nodes, collecting the data back to a single node, that is the solution viewed by the user. And of course, the most parallel overhead happens in communication. That is between every time step of the CFD solution, if we're running on steady, will take time to communicate the particular parts of the problem that are required by other processors. We'll look at some examples of this in the next class. Parallel overhead includes everything from synchronization, data communications, and of course software overhead by all the other parts of the problem. Parallel languages, libraries, operating systems, task terminations. A massively parallel problem refers to hardware that compromises a given parallel system, having many elements of processors. Finally, embarrassingly parallel means that the problem can be parallelized basically with many independent tasks. For example, if I'm in a classroom, I have asked every student to count to 10. They could all count to 10, and when they finished, they could tell me they're done. This is a parallel task. If I tell the class to count to 10 in, say, sequence, for example, student 1 says 1, student 2 says 2, student 3 says 3, etc., I cannot really parallelize that program. It can only be run in serial. This is the two opposite cases. One is where we cannot parallelize the program, that is, of counting, and the other one we can do it in an embarrassingly parallel way, that we have each student count to 10 on their own, and they can essentially do that anywhere they want and at any speed they want. There's no synchronization necessary either. With the second classification of problems, where we have multiple students count sequentially, I cannot parallelize it at all, and of course they would have to be synchronized. For example, I could not have student number 5 counting in an increment before, say, student number 2. Scalability refers to the idea that the parallel problems can scale with increasing hardware, memory, CPU bandwidth, network communications properties, and of course the parallel overhead is a minimum and decreases with increasing technology. Let's look at two types of theories and ways to account for the idea of parallelization. The first is Amdahls Law, which states that the potential program speedup is defined by a factor of the code p, which can be parallelized. So some percentage of the code can be parallelized and some can't. There's some medium between the student counting problem, for instance. If none of the code can be parallelized, we would set p to 0% of the code. For 100% of the code, if we can take all our computer code, that is the CFD, and parallelize it, then of course our speedup would be 1. We would then write p would be 1. We would then use the equation in Amdahls Law of 1 over 1 minus p, and we would get the percent speedup. A graph on this is on the right. On the x-axis is the parallel portion of the code that can be, of course, parallelized from 0% to, say, 90%. So if none of the code can be parallelized, the speedup will always be 1 by definition. That is pretty straightforward. 1 over 1 minus 0 is 1. If 90% of the code can, of course, be parallelized, and ideally there's no computational overhead, then ideally we will have a speedup of a factor of 10 if 90% of the code can be parallelized. This means that the code will essentially run 10 times faster if we are able to parallelize 90% of the code. And so if a CFD code, the object is to parallelize the majority of the code to get a high speedup as possible. Contemporary CFD codes have of course, parallelization speedup factors which are approaching 99 or 98% or higher. Now, we can modify this particular Amdahls Law today to include the number of processors. So now we introduce a new variable, which is the number of processors. P is still the percent of the code, which is parallelized, and S will be the serial fraction of the code, which is not parallelized. So for example, if 90% of the code has been taken and being run in parallel, then S would be the part of the code that's running in serial, which only would represent 10%. So our new speedup formula would be 1 over p over n plus s. Let's look at some graphs. Now, on the x-axis, we have replaced percentage of parallelization with the number of processors. And on the y-axis, we have a particular speedup. Because there's only a particular s for each p, we've plotted 25, 50, 90, and 95% parallelizations of the code. For example, if we parallelize 50% of the code and the other 50% is running in serial, we'll get this pink line. If we have one CPU, you can see the speed up of all cases is still 1. There's no speed up because we're only using one CPU for the parallel and serial parts of the code, and essentially hasn't changed. In practice, a parallel code running on a single processor will take longer than running the equivalent serial code, because of course it has a lot of additional overhead from the parallel programming libraries. And of course, if we add a number of CPUs, say 32, from 1 to 32, we increase to about a speed up of 4. Now if we add and go more CPUs to maybe 4,096 CPUs, or processors that is, then of course we still have no more speed up. So there's diminishing returns. The more CPUs you add, eventually you will not have any particular speed up. This is basically seen as a law. So you can never take any particular code and parallelize it by a certain percentage and achieve like unlimited or infinite speed up. This is very confusing. Naively, you would think that the more processors I add, the speed of the problem and its solution would go down and approach 0, or a very, very small number. This is not the case, and it's surprising to many students. Finally, let's look at the 95% case. If we take our code and parallelized it, 95% is running in parallel, and 5% is running in serial, we will get a theoretical speed up of 20 for, 2048 processors roughly. Only 8 processors would only, of course, operating at a speed up of about 5. This is very important to understand these concepts when you're choosing the number of processors or CPUs and nodes that your code is running on in CFD. Now, the idea of scalability is simple. We divide it into 2 categories. Strong scaling and weak scaling. The total problem size will stay fixed as more processors are added. If we do a parallel study with holding the problem size total and increasing the number of processors, we would do a strong scaling study. A weak scaling study where we increase the number of processors and remain the problem size on a per processor basis. The ability of a parallel program's performance to scale will be a result in the number of integrated factors. It's not this simple. It comes down to many factors that involve the hardware and of course the software and programming, and especially the type of problem we're solving. There's many of these factors can be examined here. Some are memory, the CPU bus bandwidth, communication network bandwidth, the speed and latency of communications on the network, and of course the amount of memory available to any particular machine. Parallel clock speed, the CPU speed, is important too, and of course all the parallelization libraries that are inherent in the software and system. Let's now talk about memory architectures. These are critical when, of course, looking at our clusters which we'll be using. This goes back to the nomenclature and classification we showed earlier from the 1960s. Here, we might have a shared memory machine. So, in my view, the traditional supercomputer and what I view as a real supercomputer is a shared memory machine. It might have one large block of shared memory. This could be hundreds of gigabytes or terabytes of RAM today in 2020. And every CPU, there might be thousands of CPUs, can all access that memory. This is a wonderful thing and is an easy type of program to parallelize. But as you can see, it just defeats the problem of communication between nodes. In the lower right image, we show a shared memory machine on a particular blade, but the memory is distributed. So overall, we call the system in the lower right a distributed memory machine, and the machine in the upper right a shared memory machine. Our local desktops and laptops, etc., are all shared memory. They might have multiple CPUs and multiple cores, and they can all access the same memory bank. In the lower right is a typical cluster computer like we have at many universities and supercomputers of the world. They have thousands of these nodes, and they all must communicate through the particular network interface and connections. You can see in this particular case, if the CPU in the upper left wants to access memory in the CPU in the lower right, or memory bank in the lower right, it has to send a request to get the memory from the node in the lower right, and the node in the lower right has to send it back. These types of operations are happening every time step or multiple times for every time step during a CFD simulation. You can see a CFD simulation, which has thousands of cores of shared memory, doesn't have to worry about communication at all. This means that the whole communication overhead for the shared memory machine is completely eliminated. So you might ask yourself, why don't all supercomputers today use the shared memory machine? Well, the answer is they're way, way more expensive, complex, and harder to create. The cluster systems can achieve much faster speeds at much lower prices because each particular computer is broken down into its own node and connected only through a network interface. The problem with the cluster approach, of course, is that with all the communication going on, it's harder to program and harder to manage. So let's talk about particular memory. Like I said, there's distributed memory, where the memory is distributed across multiple nodes, and it might all have the same address, but in a global scale, it has a different address. This means, of course, the local processors have to share memory. So in the upper left node, there might be a CPU with multiple cores. It shares only the memory it has on the blade. It operates completely independently, and the synchronization of the problem is done by the programmer. That is, the person who created the CFD code in this case. The network, the high-speed network, is how all the nodes communicate. And so the communication just doesn't happen automatically. It happens through a carefully controlled process of course, the programming language and its libraries that handle the communication. Now, there's also hybrid systems which use a distributed and shared memory approach. For example, down here in the lower nodes, we might see a collection of series of CPUs which are distributed. And of course, these CPUs share memory, and there's memory distributed, which would be accessed through the network from, say, one particular node. It's pretty simple. I think you're getting the idea. Now, we could also have distributed GPU computing units, graphics processor units. In the original cluster computers, which were distributed machines through nodes and high-speed networks, they did not contain graphics processors at all. For example, if the only job of the node and associated CPUs and memory, etc., is to do floating point operations, why would we need a graphics chip? Well, it turns out that graphics processors are very good at solving particular problems. Perhaps we'll talk some about GPU computing in this class in terms of CFD. Nonetheless, it could be now that with certain cluster computers are being built with multiple GPUs on each particular node. And so they're distributing the GPU cards across multiple nodes. These have the same memory distribution that a distributed computer would use. So it's a very simple addition. And certain codes and certain algorithms can take advantage of GPUs. Some CFD simulations and models and solvers can take care of GPUs, but it is more rare in CFD. This is still an emerging field, which has started about 10 years ago in 2010, when GPU computing in CFD was really starting to take off. Let's now turn our attention to discuss the fastest supercomputers in the world, which is kind of fun. Now, I pulled this data from November of 2017 and took some screenshots of the Top 500 list website. You can go to this site today, top500.org, and see the list of the top 500 publicly known supercomputers. Now, note there's some supercomputers, and these are all cluster-based, everyone in the top 500, except for a few, that are all distributed memory. The classified systems, of course, are working on defense problems and other problems of national security. It's very likely that the world's fastest computers won't appear on this list. These are just publicly known computers with published results that are collected and put in a top 500 list on a monthly basis. It's actually really fun to look at, and it helps us understand a little bit of the politics and the emphasis of research through the world. Now, the list on the right, I've taken a screenshot of the top 10. Let's just read the countries they're from for fun. China, Switzerland, Japan, United States, Japan, Japan. Look at the list today and see how the list of countries have changed in the top 10, for instance, or top 100 or top 500. The second column shows the exact type of system they used. For example, it shows its name. In the United States, number 6 is owned by the Department of Energy and is called Sequoia. It's an IBM Blue Gene machine. It uses, of course, power chips at 16C, and each one's 1.6 gigahertz. There's some customization. It's manufactured by IBM. So you can see the manufacturer of these systems. Some of these will be household names, and some might not be familiar to you. For example, they are NRCPC, NUDT, Cray, which is one of the most famous and historic names, Exascaler, Cray, IBM, which is a very famous supercomputing vendor, Cray, Fujitsu, and Fujitsu. Look at how this list has changed today on the top 500 list. The next column shows the number of cores. So this particular computer at number 1 has 10,649 1,600 cores. And then they say if we use all cores on the machine for one single problem and benchmark it, we'll obtain 93,014.6 teraflops per second, which is an amazing speed. And this is in 2017. Now, processor performance and performance in the computer should always be balanced by power consumption. Now, if you're running one of these computers, it is going to be very costly. And so they list the power used in, say, kilowatts or megawatts. At the time of writing, in November 2017, this particular supercomputer used 15,371 kilowatts. That's a lot of power. Now, a large-scale, modern wind turbine produces about maybe 1.4 to 1.6 megawatts of power. So how many would we need? We would need maybe 10 to 12 full-scale wind turbines running at full capacity to operate this computer. So you can see the expense of supercomputing is immense. And if you're using a large-scale computer for a large-scale problem, it can be as expensive as running a medium-range wind tunnel test. And so sometimes a small-scale wind tunnel test might be cheaper than using a supercomputer. You'll have to decide in your future careers what is financially responsible for your work relative to using experiments or CFD. Note that access to these types of machines is very difficult to get, and very high priority simulations are used. In the United States, a lot of supercomputing resources are, of course, used for weapons development for the nuclear arsenal by the Department of Energy. Many of the computing developments in CFD and computing itself for parallelization was also driven in the aerospace industry by CFD itself. Let's look at some breakdown in these statistics just for fun at the time of this writing, and I encourage you to do so too, from the Top 500.org website, 500.org. This is a breakdown by applications. 96.2 of the reported applications were not specified. A small sliver of that was reported as research, and smaller portions were defense. So in the order of use of supercomputers, it is reported that most of it is not specified by the group operating the supercomputer, meaning it's probably classified work. Then some people might say, oh, it's just general research, and then defense, which is a small sliver, and then, of course, aerospace, and many other types of things. So you can see there's a distribution, and a breakdown by, of course, cores and everything. We can also look at the systems and countries they come from. This is just kind of fun. You can see in 2017, 40% of the top 500 computers were located in China, 28.6% in the United States, and then Japan, etc. So this has greatly changed since 2017, and I encourage you to check out that graph for fun. And of course, now we have broken down these machines by their, of course, architecture. A cluster computer are the ones where nodes are connected by a high-speed network. They make up 87.4% of the computers, and this is increasing in percentage with time. And of course, there's the shared memory architecture, which we've discussed also, which is all CPUs and processes can access the same memory bank. You see, these machines are much more rare and expensive, but I think a joy to use. Operating systems is one of the most interesting things. The top 500 list reported operating system in 2017. This is likely very much unchanged today. 100% of the top 500 fastest computers in the world only a few years ago and today use Linux or its variant. On the right, we show the distribution and types of Linux systems, that is the operating system. Remember, your phone might be running Android or iOS. Maybe it's running OS X if you're on a Mac. It might be running BSD or Linux if you're doing something exotic, or it might be running Windows. All these machines are running Linux, which of course is free to download from the internet. There's many variants of Linux. For example, Scientific Linux is very popular. When I was a kid, I was running SUSE Linux on my little laptop in my home when I was in middle school, I think. There's other Linux distributions, like CentOS would be a free one to download if you wish. It's one of the most popular. And there's some like Red Hat, which you have to pay for with licensing. But anyway, you get the idea. They're all the same type of operating system. This is why practitioners in CFD code usually run on like a Unix or Linux type system for their desktop computer to create the grids and visualize results and interact with these clusters and supercomputers. Why do they do that? Because of course it's exactly compatible. They could be running the same operating system that the supercomputer runs. They can use the same compilers. And this, of course, eases use of communication and the compatibility of the files, that is, their binary formats between, say, desktop and a supercomputer. It's an interesting takeaway. Here's the number of cores per CPU socket. So in 2017, the majority of CPUs had 12 cores in them. In 2020, most people are running 2, 4, or maybe 6 cores on their desktop on a single CPU. Some more exact machines, of course, have higher values. This class is just a bare bones introduction to the idea of parallel computing and the most basic terminology of the field, and to give you an idea of how parallel computers, clusters, shared memory machines are laid out and how we might interact with them, and just giving you an insight of getting an idea of how the top and fastest computers in the world are being used. If you stay in the field of CFD, and you're successful in working on large-scale calculations, it's very likely that you will use one of these top 500 machines one day. That's very exciting and something that not many people can say they've done. So we've given these basic overviews and terminology. It might be a little bit shaky right now, but in our next class, we'll talk about some of this technology and, of course, nomenclatures of nodes, CPUs, cores, memory, architectural, parallelization, and communication when we look at particular types and examples of parallel programming. So we'll look at some examples of parallel programming. We'll talk about the general design of parallel programming in a general sense of how we would parallelize any particular problem or code, not necessarily CFD, but the lessons and examples can be translated exactly. Then we'll look at 2 particular examples of parallel computing for simple programs and show you their source code in MATLAB. Thank you very much for your time today. I'm Professor Steve Miller.